Hi everybody. So in the previous previous class, we have studied regarding Kelvin theorem. Okay. So and I told you the importance of Kelvin theorem, how he proved this theorem, and how he got the Nobel Prize for this theorem. So these are all the very important. So now, based on this theorem, today I am going to solve one problem. That is, so it says, a perfectly conducting fluid flows steadily only in x direction. If you are going to take the coordinate system like this is the x-axis, this is the z-axis, and this is the y-axis. The fluid is flowing only in x direction. The fluid is flowing only in x direction, and the fluid is perfectly conducting, okay, and the flow is steady. Steady means, time independent. They have given, okay, once again I repeat you, a perfectly conducting fluid flows steadily only in x direction. The fluid is perfectly conducting and the flow is steady, okay, and the magnetic field H is in the z direction only. The magnetic field is applied in this direction, okay. The velocity is in this direction and the magnetic field is in this direction. And they have assumed that, assuming all the variables are functions of x only, means, so only with respect to x, you can find the changes, and with respect to y and z, the functions does not have any variation, means the derivative will become 0 with respect to y as well as z, okay. So then we have to show that the frozen inflow condition, so I proved this, okay. The frozen inflow I told you what do you mean by frozen inflow condition? It means that, so H is a function of density only, means here, so you have to prove the frozen inflow condition is that H is proportional to density, or H is equal to, you have to prove some constant into density, or to prove this you have to show H by density is equal to a constant, okay. So you have to prove, to solve this problem, you have to show H by density is equal to a constant. Let's see how to prove this one, right? So in a perfectly conducting fluid, okay, so the flow is steady. For that, the magnetic induction equation is given by, so del cross Q cross H is equal to 0. Otherwise there will be del H by del T. Is it right? So if it is not steady, then you are going to get this term. But the problem is, they have given the flow is steady, that's why the magnetic induction will simply becomes like this, right? And the equation of continuity is given by divergence of rho into Q is equal to 0. This is also for steady. Otherwise, you can find del rho by del T. Since the flow is steady, this term also becomes 0, and this will become simply divergence of rho Q is equal to 0. Call this equation as number 1 and this equation as number 2. They have given that the fluid is only along x direction, that's why, the flow is only along x direction, that's why Q is equal to U into I. And here U is function of x only, because they have given, so not at all a functions of position, other position variables like y and z, and since the flow is steady, it is not a function of time also. That's why it is purely a function of x only. In the similar manner, so the magnetic field is only along z direction, that's why it becomes H into K. Is it right? So that's why here H is also a function of x only. H is also a function of x only, right? Now, so to this to solve this equation, you have to find what is Q cross H. Q cross H is equal to, Q means U into I, right? Cross H means, right, H into K, right? So they have only single term in the vector. That's why I am not going to write in the form of determinant. Simply you can calculate it. I cross k means write j. Okay, I cross k means j. Sorry, minus j. Because k cross I is j, but I cross k is so minus j. That's why it becomes minus j into u into h. Minus j into u into h. So this will become q cross h. Now find curl of q cross h. Curl of q cross h is equal to, now write the determinant, I, j, k, and operator del by del x, del by del y, del by del z, and the components of q cross h simply, so this is 0, this is minus u into h, and this is 0. After expanding this, look here, I into this 0, this is with respect to z, that's why this is also 0. Because it is a function of x only. That's why this component, I component is 0. Minus j component, look at there, j into, this is 0 and this is 0. J component is also 0. Plus k into, k component is del by del x of minus uh, and this is 0, minus 0, 0. So only this term, so that's why this term can be written as minus k into, so del by del x of u into h. But you know, from equation 1 this quantity is 0. From equation 1 says this quantity is 0. That's why this quantity must be equal to 0. That's why this quantity will give simply d by dx of u into h is equal to 0. Got it? So this is equal to 0 means you can write it as k, as 0 into k. By equating the k components you are going to get this one. So here instead of del I wrote it as d because ordinary derivative, only one variable. And this equation will imply u into dh by dx plus h into du by dx is equal to 0. Is it right? So you can expand this equation like so, u into dh by dx plus h into du by dx is equal to 0. Or in other words, u by h into, so you need du by dx. U by h into dh by dx is equal to simply du by dx. So by cross multiplying this you are going to get like this. I am going to call this equation as number 3. Right. Now, so this is with the help of your magnetic induction equation. Now I am going to take one more equation, that is continuity equation. What about the continuity equation? Continuity equation will becomes divergence of rho into q means what? Q means simply u into I. Is it right? Simply u into I. That's why it becomes like this. So after applying the divergence means del by del x of I plus del by del y j plus del by del z k dot rho u into I. Then by taking the dot product you are going to get simply, what you are going to get? D by dx of rho into u is equal to 0 because continuity equation becomes 0. You are going to get simply this is equal to 0. Right. Now by expanding this, as same in the case of equation 3, you are going to get rho into du by dx plus u into d rho by dx is equal to 0. Or du by dx is equal to minus u by rho into d rho by dx. Is it possible? 100%. You can write like this. But what about du by dx? Du by dx means equation 3. Now substitute, so du by dx like this instead of this term. Now this equation will give So minus, oh this is minus, so u by h into dh by dx is equal to u minus u by rho into d rho by dx. So on both sides u becomes, get cancels because u is non-zero, means there will be some sort of velocity. There is no chance to study the flow when it becomes zero. So that's why, so both sides u get cancels and minus sign get cancels. Simply it becomes, so you can write this equation as dh by h is equal to d rho by rho. Is it right? So now upon integration you are going to get, so log of h is equal to log of rho plus some constant log of c, or by removing logarithm on both sides you are going to write it as h by rho is equal to constant. H by rho is equal to constant. What it means? It means that, so h is proportional to rho. H is proportional to the density. The magnetic field is proportional to density. Okay. So this is about the problem, one problem. Now I am going to prove one more very important theorem, that is so called Kelvin's circulation theorem. Kelvin's circulation theorem in MHD. Okay, Kelvin's circulation theorem in MHD. Right. So I think you have an idea regarding Kelvin's circulation theorem. You already proved in your fluid mechanics. Okay. So there you proved that. So what is the statement of Kelvin's circulation theorem in fluid mechanics? So it says that the rate of change of circulation over a closed circuit is zero. The rate of change of circulation over a closed circuit is zero. So that is the circulation in, so Kelvin's circulation theorem in fluid mechanics. In MHD, what here we have to do means, the Kelvin circulation theorem is not valid. Kelvin circulation theorem is not valid, means there we proved gamma, capital gamma is constant. Capital gamma is constant. But here we have to prove it is not equals to constant, means capital gamma is equal to constant, means there you have proved d gamma by dt is equal to 0. In fluid mechanics you proved it, d gamma by dt is equal to 0. But here it says that the Kelvin circulation theorem is not valid in MHD, means you have to show d gamma by dt is not equals to 0. Okay, so that is our aim. Now you know the definition, by definition of circulation you know gamma is given by, gamma is equal to line integral over a closed contour C of q dot dl. Q dot dl. This is by the definition of circulation. You can write the circulation as gamma is equal to line integral over a closed curve C of q dot dl. Right. Call this equation as number 1. Right. Now, so differentiate this equation. By differentiating this, you are going to get, so d gamma by dt. D gamma by dt is equal to line integral over a closed contour C of dq by dt. dq by, idನ್ನು ಬೇಕಾದ್ರೆ ನೀವು ಕ್ಯಾಪಿಟಲ್ ಬರ್ಕೊಳ್ಳಿ, d gamma by dt is equal to, so dq by dt dot dl. Is it right? Call this equation as number 2. Now, so you have to take the substitution for dq by dt. So with the help of your momentum equation for the classical MHD, right? So in the classical MHD means for a perfectly conducting fluid, the momentum equation is given by rho into dq by dt. Rho into dq by dt is equal to minus gradient of p plus rho into g plus mu into j cross h. Mu into J cross H. This is the momentum equation. There will be no viscous term for classical MHD. Right. So now you have to find all these terms in the form of del Q, dq by dt. Then you have to substitute in this equation. Let us see how to find the terms, remaining terms. Okay. You know, from Ampere's law, J is equal to del cross H. This is Ampere's law. J is equal to del cross H. Now I am going to take the cross product of H on both sides of this equation. Then it simply will becomes J cross H is equal to del cross H cross H. Is it right? Del cross H cross H. Okay. But from one of the vector identity, you know, gradient of A dot B can be expressed as gradient of A dot B. So already you used it in the previous semester as well as in this semester also. One of the vector identity says gradient of A dot B is equal to B dot del of A, okay, plus A dot del of B, A dot del of B plus B cross del cross A plus A cross del cross B. Okay, this is the vector identity. Here, so it look here, del cross H in the sense in both A and B place you can so have H. That's why replace A as well as B by the vector magnetic field H. Now this equation will becomes gradient of H dot H means H square. H dot H means H square. This is equal to H dot del of H, okay, plus H dot del of H plus H cross del cross H, okay, right, plus H cross del cross H. Now you can find there will be two terms. This is, these are the two terms and these are the two terms. So by simplifying this, you are going to get, so gradient of H square by 2 means there will be 2 times, I cross multiplied 2, then it will become H dot del of H plus H cross del cross H. Now, so by replacing the terms, I am going to take this term to this side, then it will become negative sign. To avoid the negative sign, I am going to write, so A cross B instead B cross minus B cross A, right? Then this term will becomes del cross H is equal to, by sending this to this side, that will become H dot del of H minus gradient of H square divided by 2. Okay. Now, so by substituting this term in here, in this equation, your J cross H will become these two terms. Is it right? That's why J cross H will becomes simply H dot del of H minus gradient of H square divided by 2. And also the force are conservative, that's why you can write G as, so minus gradient of some scalar quantity, that can be written as some omega or any phi or anything, okay, minus gradient of this one. Now equation, this momentum equation will becomes, I'm going to cross multiply rho also here, then that equation will becomes dq by dt is equal to minus 1 by rho into gradient of P plus G plus mu by rho into J cross H. Okay. Now replace the terms. So what we obtained here, then this will become dq by dt is equal to minus 1 by rho into gradient of P minus, instead of G, you can write it as minus gradient of omega, okay, plus mu by rho into, instead of this term, you are going to express as these two terms, then this will become h dot del of h, okay, minus mu by rho into gradient of h square divided by 2, right? So now, so you have to take the gradient operator outside from this as well as from this, but you know, so instead I am going to, unless I am going to send this term to this term inside the operator, it is not possible. That's why you have to take the condition that the flow is barotropic. Barotropic means pressure is a function of density, and the frozen inflow condition just now we proved means magnetic field is a function of density. That's why, so you can write minus 1 by rho into gradient of P as minus gradient of integration of dP by rho. After derivative, your pressure remains, it come outside. Similarly, so 1 mu by rho into gradient of h square by 2 can be written as gradient of, right, derivative of, integration of derivative of mu into h square divided by 2 whole divided by rho. You can express like this. Then, so these, from these three terms except this one, you are going to get dq by dt is equal to minus gradient of pressure term, so integration of dP by rho, okay, plus, so omega plus magnetic term, this term will become integration of d of mu into h square divided by 2 whole divided by rho, okay, plus mu by rho into h dot del of h, h dot del of h. Now substitute this term, I mean this equation, in the derivative of circulation d gamma by dt is equal to line integral over a closed contour C of, ಏನು ಬಂದಿತ್ತು ನನಗೆ, dq by dt ಅಂತ ಬಂದಿತ್ತು. ಸೊ ಅಲ್ಲಿ you have to substitute all these things, right? ಏನಾಯ್ತು, minus gradient of integration of dP by rho plus omega plus integration of d mu h square divided by 2 whole divided by rho, okay, plus integration, line integral over a closed curve C of mu by rho into h dot del of h into dl, I mean dot dl, here also dot dl. So here, so you can apply the Gauss integral theorem by applying this, I mean sorry, Stokes theorem. You can apply Stokes theorem, you can reduce this to, so surface integral, then that will become surface integral of minus curl of gradient of, ಈ ಒಳಗಡೆ ಏನು term ಇದೆ, same terms, right, same terms, okay, into ds plus, it is as it is, line integral over a closed curve C of mu by rho into h dot del of h dot dl, okay, dot dl. But here curl of a gradient operator is always 0, that's why this total term get vanishes. Then the remaining is simply, so ಏನು ಉಳ್ಕೊಳ್ಳುತ್ತಪ್ಪ ನಿಮಗೆ, d gamma by dt is equal to line integral over a closed curve C of mu by rho into h dot del of h in dot dl ಉಳ್ಕೊಳ್ತು. Okay, now look here, in fluid mechanics you can't find magnetic field, means there will be the absence of magnetic field. Absence of magnetic field means h must be equal to 0. H must be equal to 0 means this integral gives d gamma by dt is equal to 0. That's why gamma is equal to constant. It proves the Kelvin circulation theorem in fluid mechanics. But in MHD, H must be not equals to 0. H must be not equals to 0. Means in MHD, there will be the presence of magnetic field. There will be the presence of magnetic field means H is not equals to 0. H is not equals to 0 means there will be no chance to become the integration of this must be equal to 0 means d gamma by dt, so must not be equals to 0. Therefore, so it shows that Kelvin circulation theorem is not valid in MHD. Okay, so this is the proof regarding Kelvin circulation theorem in MHD. So ಇದನ್ನ ನೋಡ್ಕೊಂಡಿರಿ. Tomorrow we can discuss with the new concept. Take care. Thank you.